Next, we look at what is known as the Black-Scholes equation. It's one of those it was developed by Black, Merton, and Scholes, and I think Merton passed away before the Nobel was given, and so two of them got the Nobel for that, right? It's one of the things which sort of has really affected the banking industry, right? Banking and derivatives and all these markets. Because before, say, this, mathematics creeped into this option pricing and trading. Trading was just done by traders, right? So someone is willing to buy, someone is willing to sell, and that's what the domain of trading was. And suddenly now there was all this, stochastic calculus coming into picture, which is very different from what you would expect from a trader, right? And to be honest, even now traders wouldn't know, you don't need to know Black-Scholes equation to start trading. The whole idea of the Black-Scholes is because this was one of the questions I posed in the morning, where I said that you can see the price of an option, right? So like a stock, if you want to buy the stock of State Bank of India, you see the stock price at in the exchange, and you pay more or less the same price, right? So there would be some fluctuation in the time you execute your order and the movement in the market, but more or less it's the same price. Similarly, for the options, you see the price of the option traded in the exchange, and you can buy or sell at that particular price. So what is the whole point of having an option price formula, right? So the what it connects to is the other slide that I had, which was, can option price be made risk-free, right? So we know that the option payoff is nowhere certain, right? So if you have an option on a stock, you could end up on the maturity date deeply in the money, so you can make a lot of profit, or you could end up in a zero, right? So you do not know where you are going to end up, so your cash flow is not certain, right? So that was, if your cash flow is not certain, you should ideally not use the risk-free rate, right? So the same rate that you are using for discounting or incrementing your money in a bank account, how can you use the same process for option pricing, right? So that was achieved by this Black-Scholes framework, where they came up with a way by which you can make options risk-free, right? And that what the technique that is used is what is known as dynamic hedging, which says that you can set up a portfolio which will exactly replicate the movement of the option, right? So you would have an option which will go up, and the portfolio value will equally move, and its value the increment will be precisely the same as the option price would have moved when the stock price changes, right? And then this results in we start from a stochastic differential equation, and we end up with a partial differential equation, and the solution of that would be your option pricing formula. So this is what we now look at. So before I start with this thing, I just want to again make clear what we mean by the value of an option, right? So you have a stock, right? So let's say it was the stock of IBM, right? And its price is going to change over a period of time, right? So this is today, right? This is 30th May, let's say. And this is, say, 1 month from now, 30th June, right? So let's say the expiry of the option is 30th June. The price of the stock would change irrespective of what the expiry of the option is, right? It will change irrespective of that. And here you have an option that was created, right? So basically, option is nothing but a function of the stock of IBM, and the value of that stock, that option, would depend upon the price of the IBM stock, right? Why would that happen? Because let's look at the maturity. Let's say the strike price was 100, right? and today the price of IBM stock is 100, right? So sitting here, what you are looking at is in expectation, where are you going to land up, right? So if you know that you're going to land somewhere here, the stock price of IBM is going to land somewhere here, then the value of the option would be positive, right? And if you think in expectation it's going to land somewhere here, then the option of the value will, option of this value of the option would be, this is a strike and it's call option, say 200 and this is 50, right? And this is the strike price. K is equal to 100 is the strike. So if on 30th June, if the IBM price falls somewhere here, what would be the value of the option on that day? 0. It won't be negative, it will be 0, right? Because what you can do with here is say that I'm not going to buy it at 100, right? If it is at 200, you will buy it at 100 and you will make an instant profit of 100, right? If you are somewhere here, right? So you're not right now at the expiry, but you are somewhere close to the expiry and the price of the option is say 150, right? Then what will be the value of the option? Will it be positive, large or small? What would your best guess for the option price be? So this is say half a day, right? There's half a day to expiry and you see that the price of IBM stock is 150. The strike of the option is 100. What would be the value of the option? So it's going to be positive, right, for sure, and it's going to be around 50, right? So it can be greater, because there is a very small time interval here, so the chances of the stock price changing a lot is not going to be too much. So the price is going to be somewhere around 50 and so on. So if you move somewhere here, there's more and more uncertainty and the value of the option is going to increase, right? Because you don't know where you're going to land up. And that's why it's more valuable, right? So especially, so depending upon where your expectation is, right? So if you know that if you start with something which is here and the strike is somewhere very high up, then the value of the option is going to be 0 because it's unlikely that you'll cross the thing. But given the same price in this time horizon, if it is you are here or here, this value is going to have a higher value than this one because there is a longer time to maturity, which adds up the uncertainty in your expectation of the stock, and that's why you don't know where you're going to land up, and that's why the price of the option can be higher, right? So at this point it was 50 and so on, and then here there will be an option value, right? So all through this fluctuation of the IBM stock, the price of the option would also be changing, right? And you want to find what is the relationship between the price of the IBM stock and the option price, while also accounting for what is the time to maturity, right? Because we know that with maturity, the price of the option sort of becomes more and more deterministic, and at the final time, at the expiry, you precisely know what the option price is, right? So we know that the option price is depends upon the stock price, right? Because that's what is finally going to give you the payoff, whether it's going to be profitable or not. We also know that it depends upon the time to maturity. And the third thing that we know is that it would depend upon the volatility of the stock, right? So at this point, when we said that this price of the option is going to be 50, if we knew that the stock is a lot more volatile, right? So it could go somewhere here or here, the option price will be higher, right? Compared to a stock which we know is definitely going to be somewhere in between this region, right? Compared to a stock which would be somewhere in between this region, this one is more certain, so the option price is smaller than something where the option price is more uncertain and will have a higher value, right? So these are the things which we know intuitively. What we are going to do is construct a portfolio which is going to replicate this, whatever is this dynamics of this option, this portfolio is going to follow that, right? And because the two values will match each other, right? There is going to be no risk in the combined thing. So the option plus this artificially constructed portfolio, there's going to be no uncertainty in this combined aggregated portfolio, and that's why you can discount it at a risk-free rate, right? So this is what we are going to achieve through these coming few slides, yeah? So consider you have a portfolio which at any time has a value denoted by xt, and the portfolio has two components. So one is you invest the cash in a bank account, and the other is you have some stock holding, right? So you got some money, and you decided that part of that money I'm going to put it in the bank, and part of that money I'm going to use to buy a stock, right? And what is the quantity of that stock is going to change every day or every hour. But these are the two constituents of the portfolio, right? So the stock that you are going to invest in, you assume follows this model, right? So this is the geometric Brownian motion that we looked at earlier today and had derived the closed form solution to, right? So the stock grows at a rate alpha, right? In expectation, it grows at a rate alpha and has a noise because we do not know what the stock is. There is a noise term in the stock, and that noise is modeled using this Brownian motion. And there is a volatility term sigma, which gives what is the magnitude of the noise, right? So if there are two stocks which are identical, but one has a higher volatility than the other, then the sigma will be higher for that one, right? Typically this alpha is difficult to measure, right? So I think in your time series analysis, you would have seen how you can measure this alpha using some ARCH process, ARIMA process, right? And you had modeled the sigma using the GARCH process. So you know that they are not quite accurate, ARCH and GARCH, right? You just make an estimate and you miss the estimate sometimes. In this thing, the good thing is that you wouldn't have to actually worry about alpha. You'll see that slowly this alpha will just vanish from the equations, and it will be replaced with something which is known as R, or the risk-free rate. And that is the rate at which your money grows in a bank account, right? So there is no uncertainty there. You do not need a sophisticated ARIMA to know how your bank account process is going to increase, because you know the rate at which it is growing, right? So if you deposit your money in a fixed deposit, you know at what rate it's going to increase. So at each point of time t, let's assume that the investor holds delta units of the stock, right? So it's a function of time. So you will be changing the number of units of stock you are holding at every time interval. This process delta t will look similar to the process we had seen earlier on, right? So this discontinuous process, which is constant between time intervals, right? So if you buy certain stocks today and you update your stocks tomorrow, the number of stocks you hold are constant during the day, right? So if you buy 10 stocks today, it will remain 10, and then tomorrow you say that, okay, 2 more stocks are required, so your delta t at tomorrow becomes 12. So today it will stay 10 and tomorrow it will stay 12, right? So that is the delta t process. Delta t can be random. It's sort of random because it would depend upon the stock price that is there, and based on that you will decide how many stocks you are going to buy. And it is adapted to the filtration of WT, right? So it depends upon the stock price, which in turn depends upon WT. So if you have invested delta T in stocks, so the cash value of that is delta T times ST, right? So at that point of time, whatever is the stock value, so if you have 10 stocks of IBM, then it will be 10 times whatever is the price of IBM stock at that particular instant, right? And the amount of money that you have invested in the money market would then be XT minus this delta T ST. right? This was the total cash you had, of which you put this in the stocks, and this is what you were, xt minus delta t is what you have been left with, and this is now in a bank process, right? So in a bank, this xt, how would this change with time? Yeah. So if I write the differential equation for that, it would be, if I call this y, this whole thing as y, dy is equal to r times y times dt, right? So in a small interval dt, it will grow at the rate r, right? So in a small time interval dt, your combined portfolio, which has a stock component and money deposited in the bank account, will change like this, right? So this delta t st will change because the stock price has changed, right? So the stock price has changed in the small time interval, and that change is given as dst. And your bank account process would have grown at the rate r y dt, right? So this is straightforward. So the total change in your portfolio is then equal to dxt is equal to the change in the value of your stock holding plus the change in the value of your bank account. And what we do then is we had made an assumption on DST, right? That we assume that there is a model which this DST follows, and we substitute that DST here, and this R times this thing, right? And then you rearrange the terms, and you get terms with DT. You get terms with again DT, but here it is related to SC. So this is from the bank account process. This is because of the stock process, and this is the noise in the stock term, right? So this is the rate at which the risk-free thing would grow. This is the rate at which the risky stock will grow, and this is the noise term in the portfolio, right? So this is what would be the change in your portfolio. Right? You can also write the discounted process of this thing, right? So right now we have just looked at dxt, one second, dxt, but now we are looking at what is the discounted price of this dxt, right? So the idea is that what we want to do is we want to construct, there is an option which is going like this, and there is a portfolio. So this is the option, let's say OT or CT or PT, depending upon the kind of the option. And we want to have a portfolio which will go exactly opposite to this one, right? And it is such that at any point of time, this one, it will match this thing, right? So at each point of time, the values should be the same. So on future dates as well, its value is the same, right? So if you want to compare two cash flows on a future date, what you do is you first bring it back to the value today, and that you do with this discounting term, e raised to power minus RT, and whatever is the value at the future date, right? So you want to compute this, and this using this ETOS process, where you say this is a function of t and xt, where xt is stochastic, would be ft dt plus fx dx plus f double dash dx dx term. And wherever the dx dx term has the dw term, you will put dt, and all the other terms will be 0. And similarly this thing, right? But in this case, you don't even have to go there because f double dash x is already 0, right? So what you get is minus r xt dt plus e raised to power minus rt dxt, right? And you substitute the dxt that you had obtained in the previous slide, and you get this expression then, right? So so it's not significantly different from this term, except this r xt dt term, which term drops off? Yeah, r xt dt term sort of drops off, right? This term would drop out. Right, so that was the evolution of any portfolio which has some stock holding delta t at a different point of time and remaining in cash. Now we look at a call option. So it doesn't really matter if it's a call or a put, but for our example, we take it as a call option. So you look at a European call option, which has this definition. And its value at capital T is known, right? So the boundary condition is known and is equal to SC minus K plus. And what we want to find is the value of this option at any point of time T, right? So this we know will depend upon the time to expiry, which is capital T minus T. It will depend upon the value of the stock at that particular point of time. It will depend upon the strike price that you've agreed on. And it would depend upon the model parameters, that is R and sigma, right? Which are, so you had assumed that SC will follow a particular model and the option price would depend upon those model parameters, right? So what we can do is we can write this, say the price of the option as CTX, right? Where X is the stochastic thing, which is this ST process, right? And what would be the change in the option price? So, DC, this will depend upon this Ito Dublin formula. Yeah? Yeah? Yeah, you can do that as well. But what you will see is that you get a nicer expression if you discount it back. But if you discount and get the same value, or you do not discount and look at the values at those particular point of time, they should be equal, right? But the thing is that the expression that you will get is, more easy, better compact expression than the other case. Okay, so for this CTX function, if you want to compute DC, right? So the change in the value of the option because of change in time and change in the stock price, you have to use the Ito's process, right? And that will be right. So this would be the partial differential equation for DC, and this is what we see here as, okay, yeah, so it's the same thing here. So DCTST using the Ito Dublin formula would give you derivative of C with respect to times dt, derivative of C with respect to ST times DST plus this term that comes from the Ito Dublin formula, which is half second order derivative with respect to ST, DST, right? And next what you do is you substitute DST and in these places, and finally you would end up with an expression which is equal to this thing, right? So it will have this in the dt term and it will have this in the dw term, right? Okay, so what we wanted to do was we compare the discounted, so the change in the option price, if the change in option price here and here are the same, or at any point of time are the same, so the change in the option, if dc is equal to dx, then you can say that this x is perfectly hedging c, right? So if there is an increase in the c value, this x will also increase, so you have money to pay out for the option, and if it goes down, then x will also go down, and so on, right? So what we do then is, because we wanted to compare the t0 values, we would do again this e raised to power minus rt term. Sorry. And this will result in an equation which is pretty similar to the previous one, but e raised to power minus rt term. Yeah. So so what is the thing? So when you sell an option, you will get some money, right? Because you're not going to give someone a right without charging them anything, right? So if you sell someone that see, you want to buy my house 1 month from now, you can buy it at this price, or you do not buy at all. Depending upon how the prices fluctuate in the market. If you give someone this right, you're not going to give that right for free, right? So there is going to be a value for that thing, and that premium that you charge for giving that option is what is the option price at T0, right? And this whatever initial amount that you get, you then use that amount to set up your hedge portfolio, right? So this was X0 was the cash that you got, and now what you did was that some of that cash you used to buy stocks, and the other amount, the other bit of that cash that you had, you put it in the bank account, right? So this corresponds to this portfolio that we were looking at, right? So it starts with X0, and then you put some in the stocks and some in cash. And the aim of this portfolio is to, at each point, replicate this, whatever would this C value be, right? And this will happen only if the change in the portfolio value is equal to the change in the option value, right? So when this holds, right, for all t in 0 to t, right? And from t equals to 0, you know that x0, you know what it would be, should be equal to the price of the option, right? That and for any other time, so for t0, x0 should be equal to the option price at t0, and for any other time, we compare the LHS and RHS for these two expressions that we have already derived, right? And this would result in something like this, right? So you have, this is for the portfolio, and this is for the option, right? You have a dt term here and dwt term here. You have this as dt term here, and you have this as dwt term here, right? So first we look at the dwt term, right? And what you see is that if you set delta t is equal to this partial derivative of C with respect to the stock price, then on both the sides the dwt terms would cancel out, right? You note that this dwt term is the only term which is bringing uncertainty into this picture, right? So if you always hold the stock price, no, the number of stocks that you, the delta t as equal to dc by ds, right? If you have delta as this, then the dwt terms on both the sides would cancel out, and what you would be left is only the dt terms, right? And this is what is known as the delta hedging rule, that the amount of stock that you hold in your portfolio in order to hedge your option position is the first order derivative of the option price. And in that case, there is going to be no uncertainty because all the dwt terms have gone, so everything is certain here. And therefore, what you should see is that the discounting term that you will be using should be e raised to power minus RT, right? And that alpha term should sort of vanish, right? So this is what we see next. So now we take delta t as equal to this thing, and we substitute in, compare the dt terms. So you have alpha minus r, this thing, is equal to the other side for all t and t terms. And then if you see that the alpha terms are all cancelled out, and what you are left with is this equation, right? So you have the partial differential equation of C, which has no stochastic term in it, right? And this is what is the Black-Scholes formula for option price, right? So you started with a stochastic differential equation, which has a dwt term, right? The uncertain parameter. And now what you are doing is you are ending up in a partial differential equation, which has no uncertainty. So if you solve this equation, you get the value of the option at each point of time, right? So you can get the value of the option at any time t. What you also get from this framework is, if you want to hedge this option position, what you have to do, and that is at any point of time, you should have a portfolio which has some money in bank account and some money in stocks, and the number of units of stocks that you are going to hold is equal to the partial derivative of the C, right? If you follow that hedging rule, then there is no risk in holding the option. So as the option will move, your portfolio value will change accordingly. And at the final time when when the option expires, your portfolio value will have enough cash to pay out for whatever is the money that you need to close your option position. Right. How would you solve this PDE? In this case, it turns out when you have a simple European option. Yeah. What? So there is a connection between them, right? So because you have entered from SD, you have come to a PDE, but the way you have derived it is not the same way, right? But you can reach to the same conclusion using Kolmogorov backward equation. Sorry. For non-standard cases, right? So in this case, the boundary condition is quite simple, right? So you have a boundary condition which is which looks like something like this, right? And then you can solve even in a closed form way, but quite often the boundary condition is difficult to model, right? So for example, you have options. So they are not known as option, they are called as barrier options. So these are options which are designed in a way that if the stock price doesn't cross certain boundary and then ends up in the money, then you get some money. Otherwise, the value this option will have no value, right? So you would have two boundaries, right? So lower upper boundary, and if the stock remains between this boundary and is greater than K at this point, then you will get a payoff, else your cash flow is going to be zero. So in this case, because it has crossed this boundary, the cash flow is going to be zero at this point, even though it has entered in the money region, right? So if you have more complicated options, then you do not have closed form solution, and then we would like to use some numerical scheme to solve the Black-Scholes equation. But for the simple case of call option that we had considered, you also have a closed form solution which you can directly plug and get the value, right? So but for a more general setting, if you want to solve this PDE, what you are going to look at is the terminal condition, which is at capital T, the boundary condition when X goes to 0, so when the stock price is close to 0, and boundary condition when stock price goes to infinity, right? And sometimes it helps to make certain transformation in the stock price process, so that is PDE has a better form, and you can use a general solver which are like much more optimized than if you write your own solver, right? Right. But for a simple case, there is a closed form solution for this option price, and it's given by this expression. Basically, you need to find out this D plus and D minus term, which are a function of the volatility of the stock price that you are that underlies the option that you are going to price, and N is the cumulative CDF of normal distribution, and yeah. So basically, this would be the value of a call option, right? And anything else here? So this is the value of a call option, and you want to find the value of a put option now, right? So you want to go from this expression and you want to find the value of a put option. So either you can solve the PDE again and you get the value of a put option, but sometimes what you do is you use what is known as the put call parity, which I'm going to discuss in the next few slides. But so far, is there any doubt or question? Yeah. Why not solve the? So if you basically you want, ideally what you want is a closed form expression, right? Why do you want a closed form expression or a solver which is which is very fast, right? And why do you want to know that is because typically the use of this formula is you want, so someone wants, you are a market maker, which means that you are buying and selling, both buying and selling. So you have to give both the quotes. So at what price you are willing to buy the option and what price you are willing to sell the option, and you will get requests at microsecond level, and you cannot start solving a massive PDE or stochastic differential equation to give a price every microsecond, right? So you need a very fast solver, and that's why it's the ideal thing is to come up with the closed form solution. And even in this closed form solution, I think people work out ways in which this expression can be evaluated really fast. But yeah, that's more or less the reason why you would want to get into this solution, right? So the last and the final thing in this in the Black-Scholes derivation that we are going to talk about is what is known as the put call parity, and it brings back our thing where if you have a certain cash flow, you know that you are going to discount it at the risk-free rate, right? So we start with what is known as a forward contract, right? So a forward contract is something where you buy a stock at fixed price K on a future date, right? So it's very similar to an option, right? So what is the difference between a forward contract and an option? You have an obligation here, right? So even if the stock price goes below K, so you can buy the stock in the market at a cheaper rate, but still you would have to buy from this guy at a higher rate, right? So the value of this contract can be negative at the expiry, right? So if at any point at the expiry, the payoff of this forward contract will look something like this. Right, and it can be shown that the value of this forward contract at any point time t will be equal to the value of the underlying minus e raised to power minus r, whatever is the maturity, times the agreed price at which you are going to buy it at the future date, right? And how you can show that is by a no arbitrage argument, which means that if you have a price other than this, you can for sure make a profit, right? So can someone see why, if the price is not equal to this, there's going to be an arbitrage? So okay, let's take an example where the forward price is lower than this expression. Right, so this is the expression, and say this expression, if you evaluate it right now, it comes to 100, and you see that there is a forward contract being sold at 90. So how would you for sure make money in this case? And sell what? Yeah. No. So from the market price is 90, right? This is the market price of the forward contract. It's 90. While the formula here is giving the price of the forward contract to be this, right? So if you want to sell it back at that point of time, you will only be able to sell it at 90. Right, so what you see that the market price is lower than what you expect the price to be. So what you will do is you will buy this this forward contract, right? So what this forward contract gives you is at say capital T, you will get one stock at say some strike of 100, right? So at some K. In order to buy this one, you would have to borrow some money, right? So you borrow money from the bank, right? So you borrow 90 rupees from the bank, and at the end of the period, you would have to return the money, but that would be equal to 90 e raised to power RT, right? This is what you would have to pay to the to the bank. And at the maturity, you will be able to buy at K the stock which so you have to pay this thing. Right, and so what you see is that this is what you have to pay the bank, right? And this is what your payout from the forward contract is going to be. This would be the value of the forward contract at the maturity, and therefore you see that you're always going to make profit in this case, right? So the point is that if the forward contract is not equal to this, there is an arbitrage opportunity which can be immediately realized. So you do not have to wait. You can just lock in your profits by entering into this combination of trades, right? Now, this argument can be used to find the value of a put option, and the reasoning behind is quite straightforward. So how would the payoff look if you buy one call option and you sell one put option, right? So put option has a payoff which looks like this, and call option has a payoff which looks like this, right? In both the case, you have bought put and you have bought a call option, right? Why does it look like this? Because if the value of the stock is greater than the price you have to pay to buy it, you make immediate profit. And if the value of the stock is less than the price you have agreed to sell in, you make an immediate profit in the case of put option, right? So if you buy a call option and you sell a put option, what would the payoff of a sell option look like? It would be something like this, right? It's just the opposite of this one because you need to pay the other side. You're on the other side, so it would look like this, right? And the combination of these two, when the strike are the same, what would it look like? It would be equal to this, right? So if you sell a put and buy a call, the payoff is equal to this thing. Do you recollect this payoff from the previous slide? This is the payoff of a forward contract, right? And we know that the value of a forward contract at any point of time. So if you can artificially construct a forward contract using a put option and a call option, right? So the value of the combined call and put option should be equal to the forward contract, right? So what this leads to is that the price of a call minus price of a put is equal to the price of a forward contract, right? So this is the expression CTSC minus, so this is true at capital T, but because it's a certain equality, you can discount it at any point of time and they should be always equal. So at any point of time T, the forward contract value is equal to the call price minus the put price when both call and put are on the same strike, right? So using this, you can always calculate the value of the put option when you know the value of the call option, right? So this is also one of the nice things about this put call parity is while deriving the Black-Scholes equation, we had made an assumption, right? What were the assumptions we made while deriving the Black-Scholes equation? So one of the biggest assumptions that we made was the stock price followed the geometric Brownian motion, right? So we assume that there is a model, very simple model which exists and the stock price follows that model. But in reality, that's not the case, right? So it could be any model that the stock price could be following. So in this case, you do not have to make any assumption about the model to arrive at this put call parity, right? So irrespective of what process the stock price is following, the put call parity will always hold. And this is sometimes used for static arbitrage portfolios where people use this relation to set up their hedges, right? Okay, that's also a bit of digression, yeah. Yeah, so this is more or less what I wanted to cover in the theory part of the session. There is something more on the numerical side, but the only thing that I think I will cover here is the Monte Carlo estimation of these options. Yeah, so like I had motivated earlier that quite often you do not have closed form solution, and then that's the whole quest of all the financial engineers and a lot of people working in this field is to come up with fast numerical schemes to price the options, right? And then you have a wide range of methods that are applicable, right? So ranging from fast Fourier transforms to PDE based schemes or Monte Carlo schemes, and you want to find the ways by which you can calculate them as fast as possible. Right, and typically in many of these realistic cases, it's very difficult to have a closed form expression, so you have to deal with numerical methods, right? So there are different approaches for pricing of options using numerical schemes, and some of them that I briefly touch on are one is known as the binomial tree method, which is this is one of those methods which really brought option pricing to the realm of like basis, right? So earlier, all this option pricing theory was limited to this theoretical physicists and all these mathematicians and so on, and then because you required in-depth knowledge about STEs and things which were actually quite exotic at that point of time, right? But this binomial tree came around 1970s or 1980s, which made it simple enough for an MBA graduate to sort of understand what is happening, right? So the maths is simplified in a very basic way, and you're able to price the options. So it brought the lot of people into the realm of option pricing and understanding of these financial derivatives, and that's why it's also seen as a game changer. The other is the lattice-based method or the PDE-based method, and a lot of that came from fluid dynamics. So CFD solvers, which were designed to solve things quite fast. You could always convert the PDE that results from this Black-Scholes model into those forms and have a fast solver, right? So that's the other thing. And the next is Monte Carlo scheme, and this comes into picture when, especially when you have a very high dimensional option, right? So what do you mean by high dimensional option is, right now we considered a simple option which was on a single stock, right? But quite often you have options which are on indexes, right? So index is a combination of several stocks. And if you want to model the index option, you would have to model all the underlying stocks, right? And each of those would form one of the dimension of the solver, right? So if you have Nifty 50, there are 50 underlying stocks, and that makes it 51 dimensional problem, right? So that's really not feasible using PDE scheme, because even if you have a very small discretization, very basic discretization, that raised to power 50 is quite difficult to handle in, especially given that you want to solve it really quickly. So in those cases, Monte Carlo methods sort of. So that is another way, but what you want to typically look at is, if you are a hedge fund, to see if there are discrepancies between the index price and the stock prices that are underlying, especially when it comes to the option. So then you can, if you are looking at sophisticated trading strategies, maybe you would like to model it in that way. The other thing is, if you have constructed an artificial, a portfolio that replicates an index, which doesn't contain all the constituents of the index, then you would like to also model it in that way. So not just Black-Scholes model, because what happened was, in 1987 there was a big market crash, right? And that was attributed to the Black-Scholes model, right? So it is one of those models which got the Nobel Prize, but was also responsible for a financial disaster. So in fact, I think Scholes and Merton, I don't know, one of them, Black and Merton, they formed a hedge fund company, which, a capital fund company, which was known as LTCM, and they used their option pricing sophisticated methods there, and that company at some point also caused another financial disaster and became bankrupt, right? So there are drawbacks to the Black-Scholes model, which people realized quite quickly, especially in 1987 when there was this market crash. And one of the biggest drawback for the model was the assumption that the stock price follows this geometric Brownian motion with a constant volatility, right? What people realized was that for the different strike prices, you would get different volatility that is implied from the market, and which doesn't fit with the assumptions that were made by Black and Scholes. So right now the use of Black-Scholes model is merely to invert the option price to a volatility term, right? So you observe the option price in the market, and what you want to do is you want to represent it as volatility, and then you use the Black-Scholes formula and get the volatility term, right? That's the use of Black-Scholes model in most of the trading desks, and people have moved down to more sophisticated models where so far we had considered sigma to be constant, but then in these models you have sigma as well to be a stochastic process, right? So, or sigma is, if not stochastic, it also is a function of time and stock price, right? So depending upon the variable is called either stochastic volatility model or local volatility model, right? Yeah, so variance gamma model includes jump processes. It constructs the model by including many jump processes into the to model the thing. So it doesn't go about using the Brownian motion, but takes another approach to things. So and all these models are made to sort of fit the market better. Yeah, so I'll briefly touch upon the Monte Carlo method, and I think for the lab exercise today, Ravindra here is going to cover the this binomial tree method, right? So I think I just have a couple of slides on Monte Carlo method, right? So it's so Monte Carlo methods are used for integrating some processes, and the benefit of the Monte Carlo method is that you do not have to worry about the dimensionality of the problem, right? So we can take a very simple example. So one of the examples which is quite often dealt with is you want to find the value of pi, and you just have a random number generator, right? So how can you do that? Can anyone take a shot at it?
So this, if the random number you are generating is within the circle, so you take the fraction of numbers that fall inside the circle.
No, so I didn't get it actually. So what kind of random number are you assuming? What distribution is the random number drawn from?
Normal.
Okay, so I think you both have the similar idea, and so what you were wrong in is that you drew it from standard normal variable, but it's actually uniformly distributed random variable. So what you do is let's say this is the thing, this is 0 to 1 and this is 0 to 1, right? And you draw the random variables from a uniform distribution, so they can fall anywhere here, right? And then you try and find the number of points which would have been inside the circle, which has the diameter equal to 1, right? And the fraction which falls outside, right? So that and the probability of them falling inside the circle would be pi r square by 1, right? And so this would come out to be pi by 4. So by law of large numbers, if you take this, if you have more and more samples, the ratio of the number of points here by number of points in the total square will be equal to pi by 4. And from that you can estimate the value of pi, right? So you can actually go to the arbitrary precision of pi conditioned on you have a very good random number generator, right? So that's the challenge then. So this is the simplest example, but I'll sort of go a little bit more on this one. So you want to integrate a function f of x dx between a and b, right? How can you integrate it using Monte Carlo method? What? Yeah. So more precisely, so I have you want me to generate some uniform random variables, and between. So in this case, between A and B. And okay, so what you have to do, okay, I'll just give the solution. So what you have to do is you generate random variables xi, right? From a uniform distribution, which is between A and B, right? And then you evaluate, so you get several samples of this, let's say x 100 for R. So you have a sample of x1 to x100, and you evaluate the function f at each of these points, right? So you calculate f at xi, and you take the summation of that, right? And what you take is this. So you get the average value of xi, fxi, and then you multiply it with b minus a, right? And this would approximately be equal. So if it was f, this would be an approximation of f, which will converge to f as n increases as your sample size increases, right? Right. So what we are trying to say is that the expectation of fx, right, where x is drawn from a uniform between A and B, is going to be times something is going to be this integral, right? And why is that the case? Because it will be equal to fx. So expectation of this is equal to fx times dpx, right? And what is dpx here? The density function of this one, it's equal to 1 over b minus a dx, right? And so what you are calculating when you estimate the expectation of this, where x is from a uniform random variable, is basically 1 over b minus a times fx dx, right? And this was the integral that you were interested in, right? So if you multiply this expectation with b minus a, you will get your integral of that you were trying to approximate, right? So let me write it. Right, and how are you evaluating this expectation? You are evaluating this expectation using the law of large numbers, where if you start sampling more and more x points from this distribution, your expectation converges, and that's why you get a good estimate of the integral, right? So what is the advantage of a Monte Carlo method? So how would you evaluate it otherwise? So this integral of a to b fx dx. What is the other numerical method you will use? Yeah, right. So what you have to do is you have to discretize AB, and then you have fx, and you get this thing. That works really fine if the dimension of x is one dimensional, right? Now if you have a function which is and you need to do this. Right? So in order to discretize this for your Gauss quadrature method or Riemann integral or whatever you want to do, say for x you have say 100 this thing, right? Discretized point. Similarly for y. Similarly for z, and if you have more than 3 dimensions, the number of points that you have to evaluate sort of grows exponentially, right? And 100 is typically not enough to evaluate a function. So the number of computations that you have to do increases phenomenally, yeah? But if you have to compute the same thing using a Monte Carlo method, this thing would again be equal to expectation of f of x, y, z, whatever it is, and these drawing the random numbers for this x, y, z is again almost the same amount as you are doing for one-dimensional process, right? So the whole advantage of a Monte Carlo scheme is that with increasing dimension, you do not have to worry too much about the computational this thing. And the convergence is slow, but at least you will be able to evaluate the integral and in higher dimension, right? So the same approach is used for pricing the European option, where you want to, what are you interested in is expectation of the option value at final. This is max here, yeah? So this is what you are interested in evaluating, right? So this is the expected future payoff, right? And what we had established from the Black-Scholes world is that you can always hedge your option to make it risk-free. So if you can get the expected payoff on capital T, the option price today would be its discounted value, where you discount it using the risk-free rate, right? So e raised to power minus RT, right? So what you have to do is you want to find this expectation, and in order to find this expectation, what you have to do is you have to draw this ST, right? So you need to simulate ST, and for each of the point you have simulated the ST, you calculate what the payoff it is going to be, and you take the average of that payoff from the several samples that you have come across, and discount that back to T0, and you get the option price, right? So it's a pretty straightforward method to compute this thing. The only thing is, how would you draw the samples of ST? Right, so you want to sample ST from a distribution. So far we were looking that we could draw numbers from uniformly distributed random variable. But in this case, what would be the distribution? It's because it's not just straightforward Brownian motion, right? So there's Brownian motion plus something else to it. So you want to find the exact distribution of ST. So in the case of geometric Brownian motion, it's quite straightforward because we solved the expression for that, right? So it was S0 e raised to power r minus sigma squared by 2 t plus sigma Wt, right? And Wt we know is a normal variable with a standard deviation equal to square root of t, and it's centered around this thing. So you can take this as square root of t x, where x is normally distributed with mean 0 and standard deviation 1. What? So this came from the geometric Brownian, so this GBM process. DSC is equal to RST dt plus sigma ST dWt, right? Quite often you might not have a closed form solution to that. And in that case, what you will use is Euler discretization. And that would result in something like ST is equal to RST delta T plus sigma ST d delta, right? And this one is again a normally distributed random process, right? So in which case? Yeah. So in this case, volatility is considered constant, right? So this is for a more general setting where sometimes the sigma might also be a function of time or function of stock, and then you can use this discretization process. The only thing is that it will converge where delta t becomes smaller and smaller, right? So it has a bad convergence, but it's like more generic to implement. Yeah. What? So here we know the PDF, right? In this case. So because you know the PDF of x, right, which is a standard normal, So you would get the PDF of this one. So either you work with this, or you could even work with LNST, and then you would get a term which is A plus BX, right? And this is again normally distributed random variable. So PDF would be known in this case. And in this case, your PDF is again normally distributed because it's a sum of normally distributed random variables, right? Yeah. Yeah. Yeah, so that is one of the challenging problem that people, so quite often sampling, so this discretization part is what a lot of work goes into. So that's where you look at discretization schemes where the distribution that you will sample will be closest to the true sample without making too much delta. You do not have to go two small steps for your this thing, right? But once the steps, once the paths are generated, evaluating the expectation is not far. Although what we are talking about here, this problem is for a European option. This becomes even more complicated when you are looking at what is known as American option, where you then have an optimal control problem as well, right? And in that case, you need to do something very different in order to come up with the option price. So there are many challenging areas in this option pricing world, but this is what is the say the basic theory that goes behind each of these things, right? So I think. Yeah, so to be honest, I think the topic is a bit far from a lot of things you guys might have been working on, right? So first of all, options is something I think many of you heard for the first time today. So which sort of forms the basis of the whole talk. But what you will see is that you'll find perhaps some connection if you are going in the direction of stochastic process, and there are a lot of things that sort of fall common between especially information theory and this financial mathematics, right? So you can, I think, going forward, see some connection or get reminded of some of these concepts, and maybe some of these things might be useful for you in your research. Yeah? So this is what I have for today. The later half of the thing will be taken by Ravindra, who's going to talk about binomial tree method and also the Monte Carlo methods, right? So do you guys all have some programming language on your laptop which you are comfortable with? Yeah, so then you can have a hands-on exercise to work on the problem.